We'll try to get the things done for you to complete the homework. Okay, on the homework, I think there's a few questions about the block diagram and then about the signal flow graph, the application of the solution. I think that is the one. I try to finish the things by Wednesday. And the block diagrams, basically, block diagrams is a graphical representations of a control system. So, for people who like the graphical, for people like me, and in my way to learn something, if I form the graphical images in my mind, in my brain, then absorbing the information from the images, then that's the way I learn stuff. So I found at least the block diagrams are very useful for me to get certain insight into the control system. The block diagrams are based upon the transfer functions, and from here you can see we have introduced the transfer functions. Basically, transfer function is the relation between the output and the input. And this is the graphical representations of the algebraic equations. Y equal to G times X. That's it. So basically here in terms of this will be the generic unit component in the transfer function. Then we pretty much will apply this principle, this algebraic principle to write up the mathematical expression for any block diagram we will see. On the other side here is for your reference. This is the algebraic equations, and that's described in the S domain. So if we take the inverse Laplace, then we can get information in the time domain. Again, this is in terms of the Laplace transform, this is called the convolutional integral. Okay. If we have the function multiplied together, then we take the inverse. Basically, we explained it would be doing this. And this is called the convolutional integral. And this one can be done pretty easily if we have an explicit function. Okay, so this is the first symbols I want to show you. Basically, this is take up any algebraic operations. Again, the reading is this. The output of this operation is from the input. So, for example, the output equal to A minus B. That's it. Okay. And this one, before we go after the explicit representations, and by looking at this graph first, we can see this is we call the closed loop control system, because that is closed the loop. That's it. Okay. So this is the very typical block diagram, and actually, in many other complicated block diagrams, we will be able to always shrink, simplify into this kind of format. Okay. So for this one, let me show you how to do that one. Again, the reading is this. The output equal to the gain multiplied with whatever the input here. So we're starting from here. This is our output C. Output C equal to G times the input E. Okay, and then we can explore what is E. E basically is the taking up the operation of R minus what? R minus C. Okay. Our goal is to obtain the transfer function of C over R. This is our output, this is our command input, this is we call the error, or this is the intermediate input of this one. So whatever you name it. But our goal is to find out this one. So we can see from here we can rearrange. So C plus, we expanded this one and move the GC to the other side equal to GR. So from here you can see in this way C 1 plus G equal to GR. So therefore C over R equal to G 1 minus G. Okay, so the transfer functions of this one, this graph will be equivalent to, that graph will be equivalent to this. This is our input. the block diagram, the transfer function is G 1 plus G, and this is C over S. Okay, so therefore such a closed loop diagrams can be equivalent to this one. Okay, and you might ask me why we bother to learn the block diagrams, and again, as long as we have the input-output relation and stuff like this, then, for example, if we want to categorize the time response, just like the homework one I prepared for you, the question one is the homework 2. Okay, so basically we can take the Laplace transform and inverse Laplace transform to find out what is the response of C in the time domain with respect to this one. Okay, if you haven't started, I would suggest you start it right away for question 1, so you will see what I'm saying here. Okay, so that is for this diagram. And for this one, the difference from the previous one, if you look at these two diagrams carefully, let me compare this one and this one. What is different? This is the one we call the unit feedback control system, because in the feedback loop, this is called in the feedback loop, in the feedback path, we have the gain, the function gain. The function gain is equal to 1, and 1. So usually we didn't write it, didn't say it. But for this one, in the feedback, we have a different gain. It's called the H. And H can be sensors, H can be anything, or maybe whatever the modeling you would see. So for this scenario, then we can, let me do that here. So for this case, we can see, using the same technique, so G, again, we read from the output, and step by step, C equal to G times E. And what is E? E takes up the operation of R minus B, okay? And what is B? B is the output of H multiplied with C. So again, here we want to find out the transfer functions of this one. So from here we can rearrange. So basically this one, C equal to GR minus GHC. So therefore, C plus GHC equal to GR. So therefore, C 1 plus GH equal to GR. So therefore, C over R equal to G 1 plus GH. Okay, and so for this case, we have a little bit different system. So for that one, that system is equivalent to here. This is the our input, and this is the output. And here is G 1 plus GH. Okay, like this. And there's no fixed patterns for the feedback for the block diagrams. There's so many kinds. So here I have no way to give you an equation and how to apply that equation to solve all the block diagrams. So basically those are the principles. For each single problem, you basically do the manual scratch calculation. This should be very straightforward. And once you're familiar with it, you can skip a lot of the steps here and do quickly. Okay. So here is another general patterns. The basic components in block diagrams, and usually for myself, I didn't pay attention to those names because those are, well, it's not that useful. As long as we can do the operations algebraic calculation, I think that's fine. But here, the people like to classify, say this is for the series connections of the two blocks. and those are the parallel. For example, C equal to G1 times R plus G2 times R. Okay. For this one is C equal to G2 times this, which in turn equal to G1 times this. So then you write up here. So for the first case, for series, C equal to G2 times G1 times R. For the second one, C equal to G1 plus G2 times R. Okay. For the third one, we have done that before, so basically that is G1, 1 plus G1, G2 R. Okay. And so here provide you the exercise. So we have done this one, and here the MATLAB. Well, I don't think this is necessary, but for the newer versions of the MATLAB, it provides such a nice function if you like to use it. And so, for example, if you want to calculate this one, you simply put into command. So let me do one example here. So, for example, here for the series combinations, we have, say, s plus 1, s squared plus 2, and here is 1, s plus 3, and here is c, here is r. Okay. So here I make one example for of the series combinations. But this example will suit for all the other things. So I will show you how to write up the arguments, those things here. So for this example, say, once you type it into the MATLAB command, then here is our transfer function 1. Okay, here is our transfer function 2. So for transfer function 1, you can say the numerators of the transfer functions equal to the coefficients from the highest order, from the highest degree in descending order. So 1, 1. Okay, these are common here. You can put a semicolon. So once you hit return, the MATLAB will surprisingly display. And then in the second one, you can put the denominator den for the first functions, and that one again, the coefficients from the highest degree in descending order 1, 0, 2. Okay. For the second one, the numerator 2 will be equal to simply is 1, and then denominator 2 will be equal to 1, 3. So once you have everything set up here, you simply call up this command in series, and then put those things into here. And then once you hit return, the numerators will be the answer of G1, G2. So basically this one will be equivalent to R C. Let me multiply this is as 1 s squared 1 0 2 1 3 6 0 3 2 0 2 q 3 2s 3 plus 3s squared plus 2s plus 6. So for this one, the equivalent transfer function will be like this. So once you plug in those commands, you hit return, then the MATLAB will give you the result is this. The NUM equal, I try to mimic what you see in the Windows. So that will be 1, 1, okay? And then denominators will be equal to, from here is 2, 3, 2, 6. Those are the result you will obtain from the MATLAB. Okay. For this one, again, if you can describe your individual blocks and then using the parallel command, and again you hit return, then the MATLAB will give you whatever the result of this one. And the same thing for the unit feedback here, then like this. Personally, in my using experience, I found if I derive by my hands manually, I think this way will be quicker than running in MATLAB. Okay, that is my experience. And go back to you. So this is the exercise provide for yourself, and so those ones are we done there. By the way, this one is another command, print system of the numerators. So for example here, if you already have the two commands, and then if you say print system and NUM1, DEN1, then in MATLAB that will give you the functions. They will give you an expression is like this, s plus 1, and MATLAB doesn't have the straight line, but basically using this dash line. And then here this is s squared plus 2, something like this one. Okay, so if you want to see what is the systems you've been working on, you can utilize this command to help display these things. So once we have the fundamental information about the block diagrams and simplify the block diagrams, then we can begin to take a look at more complicated and practical ones. So this is the very practical, very typical block diagrams of certain real systems. So for example here, I would say, let me make one example here. So for example, if this is the DC motor, okay, and not the small one, the kind of big one. And to power up the DC motors, you need at least you need here the signal. Usually, say depends on the voltage control or amplitude, the current control. So basically, those are signal is way above from the computers. Okay. So usually at the user's end, we have our computer to control it. So output of the computer is so small, so we have to amplify. So here we have certain actuators, and to amplify the signals. The actuators can be mechanical systems or can be electrical system. Electrical system usually combines of the power electronics. Okay, power electronics, that means to modulate, take up these small signals and then power up into the range of the working range here. Okay, so actually here is the actuators combining with the amplifier here. So here is basically is the open loop. So it is our output. For example, say here we take up the output of the motors. Say we want to do the step motors, like the step motor, just like if using the robot. Right now, the Google motor company, they actually name it as Boston Dynamics. Have you heard about this? The Boston Dynamics, they help military to develop a lot of the robots. The robots will just have many kinds, have the main kinds, have the dog kinds, have the cheetahs kinds, you name it. And those robots are very, you will see, in a few years, they're going to change the world. The company called the Boston Dynamics. If you have time, you can Google it, and from the YouTube, you can see a lot of things there. For those robots, and they, for the human kinds, for example, they try to mimic the shape of the human. So at the joint here, they use what we call the step motors. Step motor is you give a command, and then the step motor will give you say, I want to move, say, 90 degrees, then go to 90 degrees like this one. Okay. So for example, if this is the step motor, then usually the output is the position control. So here is how much we want to sweep. So here we take up the output, say if he here go to 85 degrees only, still have 5 degrees in discrepancies, then we put the sensors like the taking motors, taking the output, and then from the sensors we know, okay, here we only have 85 degrees. Our reference input, our design is 90 degrees. So here we have 5 degree in difference. Okay, so this control the closed loop, take up the difference, 5 degrees. Then, okay, the 5 degrees still less than 5 degrees, so I ask the amplifier to amplify a little bit more to make the motor to step ahead a little bit by 5 degrees more. Okay, so that is the thinking. In the next moment, say that power up a little bit too more, say here is 91 degrees. Okay, so the sensor sense, okay, here we have 91 degrees. Here our design is 90, so here we have -1. So -1, we're asking to amplify and to reduce this step back a little bit, 1 degree. Okay, we keep moving, so eventually this one will be oscillating quickly and reach the desirable. So that is the thinking. So for this one, each system, each component, like motors, from our modeling and hopefully from reference from the textbook, you should be able to find appropriate the dynamics of the motors put here. And then you look at what kind of the actuators you are using, either power electronics or any mechanical system, then you put the modeling here. Then amplifier and say op amp, the operational amplifier, or any the PN junction, the diode here you can put here. Okay. For the sensors, and again, usually sensor is the light sensor or whatever you put here. So basically, for every single one, if you do the modeling carefully, each block will be eventually represented by a function, right? The time domain function, then you take the Laplace transform. So each block will be the function of the S. Okay, so here is actually a block diagram. We are able to allow us to do this kind of the techniques. Okay, so that is the